If we consider every phase of instruction execution takes one clock cycle, then in an ideal pipeline execution, the instructions keep on switching from one phase to the next phase in each clock cycle, leading to a smooth functioning of the pipeline. And once the pipe is filled, giving one instruction out in each clock. This is what we expect from pipelining, but there are some additional issues called hazards which will affect the smooth functioning of the pipeline, as a result of which we will not get one instruction out in each clock. We may get one instruction out in 1.2 clock cycles on the average, or 1.5 cycles, or 2 cycles, and so on. So what are hazards, or what are the reasons for hazards? In pipelining, we are trying to organize our processing unit into separate independent units such that each independent unit can take care of each phase independently without interfering with each other. But even then, there may exist some kind of dependencies between them. These dependencies can be structure-wise or hardware-wise, otherwise data flow-wise or control flow-wise. As a result of these dependencies, if we try to execute multiple instructions parallelly, it will lead to some issues or conflicts called hazards. Suppose in clock cycle 1, our instruction I1 is fetched, and after clock cycle 1, I1 moves to the decode unit, and the fetch unit, which is free now, will start fetching the next instruction I2. So in clock cycle 2, our instruction I1 is being decoded, at the same time instruction I2 is being fetched. According to our data path, decoding the instruction involves operand loading. If the operands are already available in the processor register, then it's fine. If some operand is not available in the processor, we need to load the operand from the memory. Suppose our instruction I1 needs to load an operand from the memory. So in clock cycle 2, the decode unit will access the memory in order to load the operand. At the same time, instruction I2 will access the memory in order to fetch the instruction. Hence, in clock 2, both these instructions in the different phases are trying to access the same hardware resource, memory. This hardware dependency or structural dependency will lead to an issue called structural hazard. As a result of this kind of structural dependency, both these instructions cannot be executed at the same time. And if they are executed at the same time, it will lead to structural hazard. Now consider our clock cycle 4, where instruction I1 reached the write back unit, instruction I2 is being executed, I3 is being decoded, and I4 is being fetched. Suppose our instruction I1 is this, we find the sum of B and C and store the result to A. And suppose our instruction I3 is this, we find the sum of A and E and store the result to D. If we are not using pipelining in our normal program flow, the instructions should be executed in this order. So we should find the sum of B and C and store the result to A, and that result should be added to E and should be stored to D. And in pipelining, our instruction I1 is in the write back unit, means the sum of B and C is already calculated, execution is over, now the result is being written to A. And our instruction I3 is in the decode phase where the operands are accessed, means the data from A is being accessed in this clock cycle. Hence here instruction I3 is reading from A, at the same time instruction I1 is writing to A. Hence instruction I3 is reading some data which is not yet written by I1. Only after clock cycle 4 the updated data will be available to A, then only I3 can access it to get the correct data. Hence, if we allow both these instructions to execute parallelly, I3 will be reading wrong data. This problem arises due to the dependency on data, and the problem is called the data hazard. The conflict which arises due to the data dependency are called the data hazards. Now again consider our clock cycle 2 where instruction I1 is in the decode unit and instruction I2 is being fetched. This time assume that our instruction I1 is a branch instruction. Let it be an unconditional jump instruction. Only at the end of clock cycle 2, when decoding instruction I1 is over, it will be realized that this is a branch instruction and the next instruction to be executed is actually I6, not I2. But by that time, instruction I2 is already fetched. Hence, the smooth functioning of the pipeline is affected. We need to flush this out and need to fetch the next instruction I6 again, and this will lead to the wastage of CPU cycle. And this issue which arises due to the control flow dependencies are called control hazards. So we'll discuss the hazards one by one and we'll discuss the ways to avoid the hazards in the coming videos. And before moving to hazard, we will discuss the role of cache memory in pipelining. We know that pipelining gives its best benefit if all the phases are of same delay, but practically this is not possible. Different phases or different stages will be having different delays, and if the variation in the delays is more, then we cannot get the expected speed up from pipeline. Suppose one delay is very small and another delay is very large. The clock period will be set to the longest delay, and within that clock period we are going to get one instruction out. Hence we will not get enough benefit from pipelining compared to this non-pipelined approach. So the delays within the stages should be as much close as possible. And among all the operations, the memory access operations require a lot more time compared to the other basic pipeline operations within the processor. To reduce the memory access time, cache memory can be used. And if the cache memory can be kept within the processor core itself, then the memory access time will be comparable to the time taken for other basic pipeline operations. So from now on, the memory we will be referring to is our cache memory.